Ever wonder why some AI models train like a dream, while others act like a glitchy video game? Today, we're unraveling the secret behind a breakthrough that's making training massive AI models, like the ones powering your favorite chatbots and image generators, much smoother, faster, and more reliable. Meet Deeply Normalized Transformers, DNT, a clever trick that's turning chaos into order in the world of AI. Let's start with the problem. Transformers are the backbone of modern AI, but training them is like trying to balance a tower of Jenga blocks while someone keeps shaking the table. Why? Because during training, the model adjusts its weights, using mathematical signals called gradients. These gradients tell the model what to change, but in Transformers, they're all over the place. Some are tiny, some are huge, like a roller coaster with no track. This wild behavior, called a heavy-tailed distribution, messes up the training process. Traditional optimizers like Momentum SGD, mSGD, are like drivers without GPS. They work fine on straight roads but get lost in complex terrain. That's why most researchers rely on a more advanced optimizer called AdamW, which handles these wild gradients better. But AdamW has a downside. It uses more memory, which is a problem when building super large models. So here's the big question. Can we train Transformers with mSGD, the simpler optimizer, without sacrificing performance? Enter DNT. The key idea: normalization, a technique you've probably heard of in data science, but DNT takes it to the next level. Think of normalization as a classroom teacher ensuring every student layer in the network stays on track. But DNT doesn't just apply it once. It strategically places normalization layers throughout the model, like shock absorbers in a car, to smooth out those wild gradients. Imagine the transformer as a relay race. Each layer passes data to the next, but if one runner gets a baton that's too big or too small, the whole team falters. DNT's normalization layers act as precise baton passes, keeping the data flow steady. This stability lets mSGD, once thought too simple for transformers, work like a charm. Here's the magic. DNT's gradients become tightly packed, like a well-organized library instead of a chaotic attic. In tests, models using DNT with mSGD matched, or even beat the performance of AdamW-powered models like Vi-T and GPT. And the best part? They did it with less memory, making large-scale AI more accessible. This isn't just about better performance, it's about rethinking how we design AI. By understanding the math behind gradients and tweaking the model's architecture, researchers showed that simplicity can be powerful. It's a reminder that sometimes, the most elegant solutions are the ones that make the complex feel effortless. So next time you interact with an AI, remember, behind the scenes, some serious math is keeping it from going off the rails. Thanks for watching. If you want to dive deeper into how this works, hit subscribe. Stay curious, and let's keep cracking the code on AI together.